Newton's method gives a simple way of approximating the zeros of a function with tangent lines. But what happens if the function we're looking at has no zeros at all? In this video, we'll see that it produces very chaotic behavior, but nonetheless, there are some surprising algebraic and geometric patterns if we look closely enough. First, let's go over how Newton's method works, starting with some simple examples. Here's a cubic function with 3 real roots, and suppose we want to approximate the largest root. We start with an initial guess, which we'll call x0, and then we'll look at the point on the graph with that value as the x-coordinate. Near that point, we can approximate the graph with the tangent line, and that tangent line intersects the x-axis somewhere. That intersection point should give a better estimate for the 0 of f closest to x0. If we repeat this process, we should get better and better approximations to the 0. Now to compute these terms xn, we can take a right triangle whose hypotenuse is the tangent line. The base is the distance between xn plus 1 and xn, so the n plus first and nth approximations, and the height is f of xn. Now we know that the slope is f prime of xn, and that gives us a formula relating the two terms. After some rearranging, we get xn plus 1 equals xn minus f of xn over f prime of xn. For a more concrete example, take f of x equals x squared minus 3, so that finding the roots of f means finding the square roots of 3. We'll look for the positive one here. We'll start with a particularly bad guess here, which is x0 equals 3. We get x1 equals 2, x2 equals 1.75, and already we're within a few hundredths of the true value of the square root of 3. Applying the formula gives xn plus 1 equals xn minus xn squared minus 3 over 2xn. And after some rearranging, that's 1/2 of xn plus 3 over xn. Now intuitively, if we start with x near the square root of 3, then 3 over x will also be near the square root of 3. But one of these numbers will be smaller than square root of 3 and the other will be larger. So when we average them, we should get a better approximation to square root of 3 than the original value of x that we started with. If we do one more iteration, we get 3 decimal places of accuracy. But Newton's method isn't always guaranteed to work. For instance, we might take a function like x squared plus 1, which doesn't have any real roots at all. So now we definitely won't converge to a root. If we try letting x0 equals 2, then the points we get seem to bounce around with no particular pattern. If we plot the values of x0 through x12 on a number line, they seem pretty chaotic. Notice that x12 seems to be very close to 0, and in fact it's around negative 0.007, so the tangent line at that point is going to be nearly horizontal. That means that the terms after it will be huge, well beyond the range shown here. But if we pick a different value of x0, we won't always get a chaotic sequence. So for example, if we start with square root of 3 over 3, then the next term is negative square root of 3 over 3, and then we'll bounce back and forth between those two values forever. We can get weirder behavior also, like with this value of x0 around 0.81. If we calculate the terms now, it turns out that they never go below negative 0.22. And furthermore, the signs of these terms follow a strange pattern. they go plus, minus, plus, plus, minus, plus, 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 minus, and so on. So we get a single minus sign each time, and each run of consecutive plus signs is one longer than the previous one. So what's really going on here? Well, to figure that out, let's go back to the formula for xn plus 1 in terms of xn. If we plug in f of x equals x squared plus 1 and simplify, we get xn plus 1 equals xn squared minus 1 all over 2xn. Now this looks quite a bit like the tangent double angle formula, which is tangent of 2 theta equals 2 tangent theta over 1 minus tangent squared theta. And actually, with a bit of rearranging, we can get the equation in exactly that form, with 1 over xn being tangent of theta, and then 1 over xn plus 1 is tangent of 2 theta. In other words, if we let xn be the cotangent of an angle, then those angles double each time. So we'll set x0 to be cotangent of alpha, and then xn will be cotangent of 2 to the n alpha. Now we can plot these angles and points on the unit circle. Here's the example with x0 equals 2. Now the cotangent is the reciprocal of the slope from the origin. So for example, x2 is negative but close to 0. And as we continue around the unit circle, it seems likely that we'll cover more and more of it so that the values of xn will cover pretty much all real values. Well, we won't technically reach every real number, but it seems that we'll get close to any real number at least. The cotangent function has period pi, so actually we can just restrict our attention to angles between 0 and pi. And if we scale alpha by pi, the interval becomes just 0 to 1. So let's do that just to simplify the calculations. This rescaled cotangent function has period 1, so that means the integer parts of the angles don't matter anymore. And that means we can just look at the fractional parts of these angles. Now we're multiplying alpha by powers of 2, so that suggests looking at the binary expansion, which we can say is b1, b2, b3, and so on. Each time we multiply by 2 and take the fractional part, we shift all the digits over one place and remove anything before the decimal point. That means that xn depends on just the digits after bn. For instance, if we take the digits to alternate between 0 and 1, we get alpha equals 1/3. And this corresponds to an initial value x0 equals square root of 3 over 3. And when we shift the digits over, we bounce back and forth between 0, 1, 0, 1, 0, 1 and 1, 0, 1, 0, 1, 0. So those are angles of pi over 3 and 2 pi over 3. That gives us the cycle that we saw earlier. Similarly, if we start with any rational multiple of pi, as long as the denominator isn't a power of 2, the binary digits will eventually be periodic, so that will fall into a cycle at some point. If the denominator is a power of 2, then we run into problems because we eventually take the cotangent of 0, and that's undefined. But as long as we avoid that, we fall into some cycle. We can also use these binary expansions to say more about these sequences. So if the first digit after the decimal point is a 0, then our number is between 0 and a half. And that means that the cotangent is positive there. If the first digit after the decimal point is a 1, then the number is between a half and 1, and so the cotangent's negative. So to figure out the sign of xn, we just have to look at whether bn plus 1 is a 0 or a 1. So we get this correspondence between the zeros and ones and the pluses and minuses. As an example of this, take the value of alpha that gives x0 equals 2. And we get the sequence of pluses and minuses, which matches the signs we found earlier. And you may notice the long string of pluses after the 13th digit, and that gives us that large value of x13. These binary digits also explain that strange behavior of the sequence with starting value around 0.81. Now it turns out that this value of alpha is 0.01, 001, 0001, and so on. And that's exactly how we get this weird sequence of pluses and minuses. So a single plus, then a minus, then two pluses, then a minus, then three pluses, and so on. Also, shifting the digits and taking fractional parts will never give us a number much larger than 0.1 in binary, and that's why the xn's never get very negative. So we definitely don't get a very evenly distributed sequence of xn's. Now that we've analyzed the behavior when x0 is real, let's see what happens when we go to the complex plane. The quadratic x squared plus 1 has roots at I and minus I, so it makes sense that if we start somewhere off the real line, we should get a sequence of terms approaching one of those two values. First, we need to rewrite the cotangents in terms of complex exponentials. When we do that, we get e to the 2i alpha equals x0 plus I over x0 minus I. This won't quite work if x0 is I or minus I, but aside from those values, the fraction on the right is non-zero and well-defined, so we can find a corresponding value of alpha. Now, if we do the same thing with our formula for xn, we get e to the 2 to the n plus 1 times I alpha equals xn plus I over xn minus I. And if we compare this with the formula for e to the 2i alpha, we find that xn plus I over xn minus I equals x0 plus I over x0 minus I, all to the 2 to the nth power. Now, this has some interesting geometric interpretations. If we take the absolute value of z plus I over z minus I for some complex number z, then the denominator is the distance from z to I, and the numerator is the distance from z to minus I. So if we set this equal to some fixed constant r, this says that the ratio of those distances is just r. Now here's a graph of the values we get when r equals 3, for example. It turns out that the graph is always a circle, as long as r is not 1. If r equals 1, though, then that says that z is equidistant from I and minus I, and that means that z is a real number, so we get just the real line in that case. Similarly, we can look at the argument of z plus I over z minus I and set that equal to some fixed angle theta. This represents the angle between the two segments when we connect z to I and minus I. And if this is some constant, we actually get an arc. Note here that the orientation matters, so points in the left half plane will have theta greater than 180 degrees, and points in the right half plane will have theta less than 180 degrees. Now from our formula above, we see that each time we take another term, the ratio of distances gets squared, and the angle gets doubled. So if the ratio is 1, then it will stay 1, and that means that all the xn's fall on the real line, as we expect. But otherwise, if we start off the real line, then those ratios will approach either 0 or infinity, depending on whether we start at something greater than or less than 1. And that means that our terms will approach I or minus I. So indeed, as long as we start somewhere off the real line, we'll approach one of those two values. Now let's go back to those graphs and take x0 to be on the arc corresponding to theta equals 30 degrees. Then, sure enough, x1 is on the 60-degree arc, x2 is on the 120-degree arc, and x3 is on the 240-degree arc. Then if we double 240 degrees one more time, we get 480 degrees, but that's equivalent to 120. So from that point on, the terms will bounce between those two arcs. And at the same time, they'll be approaching I very rapidly. If we also put x0 on the circle with r equals square root of 3, then x1 will lie at the intersection of the r equals 3 circle and the theta equals 60-degree arc. And then the later terms will also be at intersections between the red circles and orange arcs. Since r gets squared each time, x4 will have an r value of 3 to the 8th, or about 6,500. And to see that, we'll have to zoom in much, much closer. If we zoom in far enough, we see that indeed x4 does lie on the intersection of a very, very small circle with one of those orange arcs. Now, all this complex behavior arose from just the function x squared plus 1, but we could also try applying Newton's method to other functions as well. If we do that, applying it to higher degree polynomials or even functions that aren't polynomials, we get significantly more complicated pictures. And these pictures, the colors correspond to which zero of the function the terms approach, depending on where you start. And we end up with fractal boundaries between those regions.